changing this template and presentation. This is really a presentation to the flavor of what ionizing is. It's work in progress. So I've been working on this basically all night. I had all the figures. I didn't have any description. I found one figure. I can fix that.
Can you speak louder so people can hear?
Okay, yes, sir. I can speak plenty loud. Okay. So
one shot.
talking the flavor of ionizing. Now, haven't arranged this in the way that I change the screen easily, so I'm just going to do it this way. So this is how's that happening?
You're okay. You're okay. People are asking questions.
Okay, so my topic is what I want to get to is the fact that I have found that something called I'm calling the vortical helicity flux really controls reconnection. So we start off with things I presented before, particularly down 2 years ago, where on the upper left is with some improvements in the calculations, is plot on the outer screen is of the energy dissipation, the viscosity times the entropy for a increasing in Reynolds number. It's about a factor of 16. Well, this one's 32 now. And there's a convergence of this, rough convergence of this at about T equals 90, which is indicated with a red line. Now, I had found previously that during the phase where the first reconnection is developing, that there is actually a convergence at an earlier time, which I call T sub x, which is for graphics, it's clearly when reconnection is ended and those vortices have reconnected. I found that the square root of viscosity times the entropy converges at that time. I still don't have a reason for why that happens, but I have graphics that suggest what's probably going on. Okay, so that's what I talked about before. The other thing I found is that to get this marvelous convergence in the upper left, I had to increase the domain size as viscosity decreased. What is constraining this to happen? Well, I think it's something to do with helicity, and the graphics more clearly demonstrate that is what's going on, but I still don't have a mathematical explanation for this. So what's changed in the last 2 years is shortly at the end of 2020, I got from JFM a number of review from different editors on trefoil vortex knots, because I'm studying trefoil vortex knots. And essentially, those people are trying to say, no, Bob Kerr's done this all wrong. You're supposed to do this in period with a threefold symmetric trefoil, and you're supposed to do it everything in 2 pi cube periodic boxes. I had tried that. And on a trip to Newcastle about 2015, I sat down with Carlo Barenghi and Andrew Bagley and said, I've done this and nothing happens. I don't get any increase in the entropy. I don't get anything that looks like the experiments that I'll mention. They said, well, an experiment is not a threefold symmetric trefoil. Yeah, they have this nice threefold symmetric 3D printed object that they pull through water, but it's on a platform. The platform is generating all sorts of little spurious vortices. Why don't you just throw in an extra few little vortices around it, sort of randomly, and see if that kicks off something more? And it really did kick off something. So this is an example of the initial condition just before things become interesting. Okay, so other things I'm going to mention. I find a modest positive increase in helicity due to dissipation. A lot of mapping is coming from mapping terms of helicity and entropy budgets onto the vorticity center. So this is a new diagnostic which I want to really introduce, and I'll get some feedback on. What I got out of reviewing those other papers is that they were all mapping helicity onto the vorticity isosurfaces, and that tells you quite a bit, because you can see, even though this is a predominantly positively so trefoil has whatever range it is, a strong positive helicity. There's no negative helicity anywhere at T equals 0. But those little orange bits there are indicating where helicity just below 0 is appearing at this time. And that's really critical for the dynamics of the reconnection. So mapping terms is important, that's on isosurfaces, but you have to go one step further and really get some understanding. Where I won't get to is that when negative helicity dissipation occurs before the reconnection is complete, post-reconnection increases in the entropy can be suppressed. That's not where I'm going to get to. I have the slides if you want to talk about it afterwards, but I haven't put any words around the slide yet. Okay, this was try one on the first page. So now what I want to get, so I've mainly been talking the figure in the upper left. And now I put this note to myself to re-emphasize the fact that there's been this separation between positive and negative helicity, and the plus and minus separation is related to the strong growth of entropy for my perturbed trefoil vortex knots. And how does it happen? So I'm going to look at the entropy and helicity budget equations, and the most critical property that is the helicity flux. The helicity flux involves a gradient of the pressure. Most people don't take the effort to go and calculate, and I haven't found a use for it by and large before now either. And what I won't get to, which I just flashed up there in magenta, is plus Y symmetric trefoils, especially those with a little core profile, do not provide the type of growth that's in the upper figure. Okay, go on in time. So this is my latest helicity as a function of time. I haven't rescaled the axis on the left appropriately. This all should be initial condition with entropy of about 3.15. In some of my later plots, I've done this right. At the time of reconnection, when there's strange square root of nu viscosity entropy scaling happens, there is an increase in helicity, but it's not overwhelming. It's if I had the right scale on the left and that was about 3, it's about 0.5, and then it decays. Okay, so in the upper right is sort of where I would go if I had 2 or 3 hours to go of what is happening to the graphics during reconnection. This is just the beginning for my perturbed vortices. And the important thing that this figure shows is it shows the beginning of the formation of vortex sheets of negative helicity. It's the vortex sheets of negative helicity that what they do as the reconnection is ending, that is what drives the sudden acceleration in the entropy growth after reconnection. But this is before that. So there's this real transition. I'm making this 1.5 nonlinear timescales, and up there we have about 2 nonlinear timescales. There's a big transition at that point. Okay, so how have I added to this? So I have this comment, third bullet on the left, in these calculations, the increase in positive helicity in the upper left is due to viscous dissipation of helicity that's less than 0, that's in these thin vortex sheets. So that is the origin of the increase in the global helicity. It's not that you're creating helicity. There's been transport of helicity that creates negative helicity in the sheets, and before reconnection, helicity is a conserved quantity. So if you're creating negative helicity someplace, you have to be creating positive helicity at another place. And once all the negative helicity has been dissipated, then you can get the positive increase in helicity, and you get the vast increase in the entropy that leads to convergence of the entropy, the dissipation rates. The way I sort of look at this, if you do these calculations and they're too symmetric, and the periodic box is too close to the object you're looking at, The fuel that generates the convergence of the dissipation rate at a later time is the formation of that negative helicity. And if there's something that blocks the formation of those negative helicity vortex sheets, then you don't have a mechanism for what happens next with generating energy dissipation. And this is sort of hand waving things I'm sort of doing on the fly at this, but this is where these results are going eventually. I'm not there yet. Okay, so I like to think in terms of budgets. So one aspect of having spent a third of my career at the National Center for Atmospheric Research is I really learned the importance when you're doing atmospheric calculations, particularly mesoscale atmospheric calculations in the lower atmosphere, is you have to understand budgets of energy and temperature and potential temperature and other properties in the lower atmosphere. And when you present a talk, you better have those plots and the vertical profiles of those things, or else no one's good. Everyone's just going to turn off. Okay, so the three budget equations that I am interested in is one, the kinetic energy on the top, and then the second one is the I'm calling the vorticity squared, a small zeta, a lowercase zeta. So there is on the right-hand side, I have underlined under brace two. I have a production, which I'm going to say called Z uppercase as things go, as the rest of my slides, and the other case is the dissipation. So where we can, that's a good idea. Thank you. So I'm going to have an uppercase Z here later on. And this is the production and what everybody usually thinks about in terms of producing turbulence. How does that get generated? This is the dissipation. Where this happens is clearly where reconnection is really actively happening. Then there's this term. This is the term that is new that I've been looking at in detail. And this sort of turns out to be driving everything. I initially thought I see reconnection from the dissipation of helicity, but it's one else. I'll show you why looking at anything other than just the helicity density, which I should say here is U dot omega here. Helicity. Looking at anything except that is really not helpful on isosurfaces. So some more thoughts. So initial conditions are really important. So three things need to be to define a vortex dot, and how we do these three items differently is why we get different results. So you have to have a trajectory of the vortex. Mine are perturbed. Other people who are doing trefoils do threefold symmetric trefoils. Profile of the vorticity, including its width, I'm calling it rho, and its circulation gamma. So if I get to there, what the importance of those are be in my conclusions. And then there's an aspect of mapping. So you have this trajectory going through 3D space, and you want to map the vorticity onto a grid. So you have this thing going through 3D space, and then you have this point over here. How are you going to determine the direction of the vorticity at that point? And that's a rather delicate topic. I have an algorithm that works extremely well. It's clear that my competition in this does things different. And they don't tell us in detail what they do. It makes it very difficult to make comparisons. And then the effect of domain size, which I'm putting as a 0, because I increase the domain as the viscosity goes down. And besides the properties here, so energy is conserved by Euler and it's dissipated by viscosity. The same with the global helicity. And of course, the entropy is produced by this term over here. The other conserved quantity that's important in this, and which I'm not going to discuss much, but it's like understanding this properly might help address many of the questions that I'm going to raise. So circulation is just the velocity taken around the vortex line, a closed loop. And important other thing is the nonlinear time scale, which I have this knot, and it has a characteristic radius in that sense around the knot, not the radius for itself. I'm calling that R sub F, and R sub F squared over gamma. And most calculations that is 1, because I start off another place. Mine is 8, so I have to rescale time scales to compare with my competition.
What's that? What's
That
that?
now let me. That's just to draw them. Okay, so I have truffle on that. And so
You can raise it.
Let me see your
Raise it, yeah.
that's R sub F. So it's the definition of the outer scale of the truffle knot.
Okay, so it's the size of like the diameter, so
Yes, it's a
the
diameter.
diameter of the knot.
Right.
And gamma is the circulation.
Yes.
But it works for us, which is already something. Yeah.
Okay, so the inspiration for doing this stuff was 10 years ago, December of 2012, William Irvin from the University of Chicago decided to pass through. He was having a horrible cold. But of course, we had no mask. We've been in Paris. I don't know what it is. See, actually, a condensed matter experimentalist. Speaks perfect Italian. He has a Scottish surname. Okay, so he has these marvelous experiments where they 3D print these knots and they attach them to a trolley, I'll call it, and pull it through water. And this creates visualizations. And in this one, it created hydrogen bubbles, and you visualize, and the hydrogen bubbles congregate on the vortex cores, and you see these vortex cores evolving. And I said to myself, once I felt confident about fixing the mistakes with the controversy between me and Tom Howe about what the initial condition should be, I said, I can do this numerically, and started doing it. This was my first one. And so we have the velocity equation. You put it in this rotation term. This is something that Adam was talking about. The importance of helicity is that if helicity is large, point-wise, then this term is small. And since that's the nonlinearity, if you have a lot of helicity, the folklore is that suppresses the cascade. And it does. If you initialize with random initial conditions, but pick every Fourier mode to have one side of helicity and let it go, the time it takes for the cascade and development to happen gets delayed, but not by much. This is what reality's been doing decades, but they asked me to do this, like Jack Kerr asked me to do this in the late 80s. And I had one paper from that. I basically did nothing. That interested me. Okay. Helicity, entropy, helicity and entropy. What do I say about that? Okay, so the trefoil has almost maximal helicity. In fact, I have never done a calculation where the initial helicity normalized with velocity and the entropy is higher than the trefoil. Reconnections are relatively rapid and self-reconnecting. And for the maths people, this can be isolated in whole space, infinite R3, and I can calculate L3, the maximum of vorticity and all sorts of moments of the vorticity. And I can, this was to do with what John Gibbon was interested in, his DSIM habits. So I have a lot of that. I haven't done a lot of things. I was hoping Sarah would be here. Tell them later. So this is three quantities that have the same units. So this is the Sobolev North H2.5, and I've got better results than I had to plot. This is from 4 years ago. So it increases slightly as the viscosity goes down, the rest of it increases. Let's see, cubic velocity norms, pluses. Okay, so let's hear it. That's L3. L3 is remarkably independent. Doesn't do anything during the stages of these calculations up through the time that you get the maximum. So this is more statements on this. This is out of the talk I gave 2 years ago. There's some more notes about why listening can be important that I had just to remind myself. So the initial growth of the entropy has convergence only of the square root of u times the entropy, not your typical dissipation rate epsilon u times that. Nonetheless, my perturbed trefoils do get that about double that time. And this thing that the convergence of that seems to be closely connected for the slight increase in helicity.
When you say convergence, convergence when what happens? When it's supposed to be becoming small?
As the viscosity decreases.
And for which interval of time? At which time?
At
So at this time, one is going to converge to constant, the other one is going to zero.
yes,
Which means that basically you don't see evidence of dissipation anomaly.
not at that time.
Yeah, okay, I understand. What about that?
Yeah, there's something. This is a finite exchange of circulation. Something like that is not dissipation anomaly. It's definitely not. Okay. So to help focus on these questions, and because I reviewed several papers of trefoils in periodic geometry, I mean small 2 pi cube boxes with threefold symmetric trefoils, and I wanted to see why their results were different from mine, I had to do some new calculations, which are in 2 pi cube periodic boxes and with threefold symmetric trefoils without any perturbations. Specifically, I am referring to calculations done by Yao, Yang, and Hussein, JFM 2021. So Yao is a research associate of Hussein. I don't know where he came from in China. Yang got his PhD at Caltech in maths under Dale Poland. And then he went to Peking University, sort of brought over by Xi Chen before Xi Chen entered politics. And Zhao is, Scalo. Zhao is Scalo's research associate. Scalo is an Italian who got his PhD under not Chiliberto. See his name. A Stanford product at Kingston University in Ontario province. And then he did a postdoc at CTR at Stanford, and now is at Purdue. And he is the quote numerical expertise helping the people at the University of Chicago. It does really nice calculations of vortex shedding off of helicopter blades. It gets a lot of funding. Okay, and all these people have a nonlinear time scale 1. It's all done in 3D periodic boxes. So let's go back. My 2 figures of entropy or dissipation rate and velocity. This is what yeah. So this is actually Yao 20 and at all 2021. I reviewed it in 2020. And Yao and Hussein now have an annual review of fluid dynamics, telling us everything we want to know about vortex reconnection. And I have my suspicions about all of it, but that's not what the topic is here, or I won't get to that. And so this is my perturbed increasing domain size results. This is the results that give it this size of a dissipation anomaly. This is what they say I should be doing. And this is their result. Here's the entropy, and it has this huge decrease initially, and then it spikes. And if you actually take viscosity times these 3, at that point, the dissipation rates are the same. But this is not even at the level of the dissipation of T equals 0. And associated with that is this massive increase in the helicity, which is very different than my rather modest, weak little chain.
Just to understand. So the picture on the left-hand side done by you,
This
this
is pulled out of their paper.
And this is for different Reynolds number because you decrease the viscosity.
Right.
But it's the same box, or you change.
This is 2 pi cube periodic.
Exactly. So 2 pi cube, exactly 2 pi cube, and then just you change the viscosity, but the same box.
Yes. Okay. So these are my new calculations of 3-fold symmetric trefoils with a periodic 2 pi cube geometry. I'm taking the hint. I actually think it was Scalo who started putting helicity on the vortex tubes because I reviewed one paper of Scalo and they said this is all engineering, that you have to do some proper DNS, LES comparisons before you can publish this. Then Yao and Hussein submitted their paper and they put in these things. And I'm certain that the other reviewer, besides me, of that paper had been Yao or Hussein. And I think they got the idea from them. This is the way Fasi Hussein so it's a really good idea. And you really see that there has something going on with the helicity on the vortex tubes as we're getting up to reconnection. And in fact, if you look carefully, this is a fairly early time. This is about 1 nonlinear time scale. Reconnections at about 4 or 5 nonlinear time scales. And the 1, 2, 3 parts for negative helicity has migrated. And now it's starting to twist up the way it's going to reconnect at these places. And you're seeing a very strong positive and a strong negative. And it's across here that the reconnection is going to happen. And in this particular figure, which in the paper I'm writing, I have the proper caption for this, is that I'm using the same symbols here, 2 stars, to indicate the 2 closest points from the 2 points of loop. That's where the reconnection will happen. So H greater than 0, H less than 0. And where's the helicity flux, negative helicity flux is what matters, is located sort of in between these 2 regions. But it's driving everything. So this is 2 later times. This is a more evolved time than that one over there. when I do my various statistics from this time to this time, to this time, well, you get it changes in the magnitude of the entropy production, entropy dissipation, helicity flux, the basic profiles of all of these barely change here and there. But here, things are different. And this is when reconnection is actually happening at these three locations. And so one thing that's happening is that as reconnection is developing, these strong negatives are being sort of swept away, they're being dissipated away. And using the helicity flux and some quantities indicate where connection is happening, this is changed. And this is a bunch of slides I put in. I had a file of all this and I downloaded it. So I wanted slides. And well, these are pores that in both Yao, Yang, and Hussein calculations and Zhao and Scalo calculations after that time that is on their time of about 5. Then what happens is you separate the trefoil into 2 vortex rings, and there's a lower one that is predominantly slightly negative helicity, and an upper one that's not the other way around. The upper one side is positive helicity. No, sorry. I know what's my problem here is I switched the color table. These are old slides from about a year ago. Anyway, this is where you have a ring at the bottom and a ring at the top. Now, in one of the Chicago papers, they say that that's what they see in their experiments, but that is not what they actually present as doing this. So one of the problems with Irvin is that he is at heart a condensed matter theorist. He really listens to what the condensed matter theories community tells him he should be interested in. And they said, well, you have to get someone who does this with quantum vortices, and you have to do it with 3-fold symmetric vortice. And of course, they get this separation into one ring and another ring. But if you look at his actual images from the experiments, that is not what they see. The other problem with Irving is he's a protege of Mike Brenner. This is politics. We can talk another time. Okay, so back to my 2 figures. And what do I want to do now? Okay, so I have now my own 3-fold symmetric trefoils in a periodic box. And so I cut and spliced a couple of figures I already had on file. And here's the entropy, not the dissipation. I'm not multiplied by any viscosities here because it's irrelevant, because I'm not going to get anything like that for this. And there is this increase in the entropy at reconnection, and helicity goes up some, but none of it's as massive as these people like to see. And there's a simple way of understanding. So the first thing now is that P equals 0, the entropy decreases. And there's a real simple reason why. And I told Scalo that he should say this in his paper. I don't know if he did. It's just this. Initial condition is you have this trefoil and you paint the outside, you fill the outside with a uniform radius vortex. Okay, now take the vorticity line and take that all the way around. It's back upon itself. You take the gradient of the velocity along the direction of the vortex line, and you take that and go around and back to itself. So if you take the integral of the gradient of the velocity along the vortex line, it should come back to 0. Therefore, that's what I say here, And because the diameter, the radius of the vortex is 0, therefore the integral of that is 0. So initially, you will have 0 entropy increase or decrease. And then the next thing, let's see if I put this on the slide. These are thoughts. Yes. But in addition, what's happening is that where this term here, the gradient along the vortex line is negative, the vortex is getting squeezed. This has nothing to do about reconnection. This is an interaction on the vortex itself. It's being squeezed, and therefore the entropy, viscous entropy dissipation must increase. So you must have dissipation of the entropy because of that squeeze. So you get, for me, it's a small effect.
So I don't understand the argument with the integral of first one is 0. Why the second is 0? Why is the P 0? Is what gamma is fixed or gamma is changing?
Gamma's the same.
It's constant.
Constant along
Curve.
the curve, you know, my
If you
little,
put it outside, then it is 0. Okay, because of the other one is.
yeah, okay. Oh, so. That's something I wanted to say. Okay, that's. One thing that Zhao and Scalo claim is that as they decrease the size of the vortex, the time of reconnection happens earlier. Yao and company, Yao and Hussein don't have any calculations like that, but at a certain level, I trust their numerics better than these other people. And I've had a lot of discussions with Yao at various meetings last 3 or 4 years, and I'm pretty certain that they looked at different diameter vortices, and they find that reconnection, all the events are happening at the time, not only the time scale that I presented, and I get that truth in my fearful symmetric triplets. And so the only thing that's going on with Zhao and Scalo is they're using a engineering code with some sort of subgrid scale, this viscosity dissipation mechanism in there that's not being properly controlled. So as they make the core thinner, the reconnection happens earlier. The diagnostics that I might or might not get to are a tool that's applied to their data. But Gallo won't listen to that. And it's not my saying that, it's someone else in his particular field. How does my threefold symmetric trefoils in 2 pi cube periodic boxes compare entropy implicitly to what I said now. Saying, yeah, and now here I don't have to say I scale the time scales in a way because we agree what the nominal time scale is. And they get that's what I show you, and I get some increase. But what happens is their decays enormously. And even though I have only a modest increase in the entropy, I do not see a decrease post reconnection. And associated with that, I have this only modest increase in the helicity at reconnection. Comparison of isosurfaces. Okay, so this is an argument for why I need to look at vortex sediments, not vortex isosurfaces. Because I want to understand what the terms in the budget equations are doing. And so, yes, these are beautiful pictures showing positive and negative helicity on the isosurfaces. But if we're going to get an understanding, we have to know what the terms of those equations are. These are 2 figures I pulled out of my file last night. So the apologies that they aren't quite the same types as this. But they create the point I want to make. This is the entropy production map onto the treadmill. And yes, there are variations in red and sort of between. This is, there are points on this where there's a very bright red, but you can't see it. There's a point on this where there's a very bright blue, but you can't see it. All you see is the plus or minus. And if I look at my helicity flux, it's the same sort of thing. So this is actually more as the reconnection is starting to happen. And so the helicity flux is there, the square here. And yes, there are the variations of plus and minus, but it's nothing like that. So I decided that what I needed to do is I started understanding how to use the interpret 3D functions in MATLAB properly. Is I needed to do it differently. So here's my trefoil, threefold symmetric trefoil, and there's this vortex line that I found. I find it's useful to get the maximum of the helicity, positive helicity, and then actually map the vortex line backwards. Yao and Hussein have some very fancy algorithms for following vortices in the center lines. Which I'm not going to try and reproduce, but it's those lines that I'm going to map onto. Now, a lot of noise has been made about the fact that there are topological properties to these vortex lines. In particular, in a topological sense, you can take the topological helicity of these. It's a variation of the Gauss-Linking integral, and you can split it into a rise and a twist. And what I found previously is that the rise, which is just Bielsen, and you go through the formulas that Keith Moffitt suggested you use back in 1992, that rise is a really good estimate for what the helicity is. The topological helicity of that of a trefoil is 6, and the actual helicity is about half of it. That's because that's what the rise is. And there's absolutely no role for twist in any of this. I've not found anything. I have found absolutely zero evidence that there's any trans exchange of topological properties between rise and twist in any of the calculations I've done. However, transport of helicity, real physical helicity along these vortex lines is enormous. It's very. So I take those lines, I take those fields, 3D fields, and where I started out, so this is how I find the lines. Okay, so I have seed points, I can take the maximum vorticity, min-max of helicity. I identify trajectories using the string 3 function in MATLAB. And then I map the fields onto those lines. I first said, well, let me do this with helicity. And I've cut off part of my legend here. But here's the helicity. And what we're looking at is where 0 is, well, actually, so the 0 line is at 1, okay? So what we have here is the difference between the yellow starting there and down to red. You have to think about this is above this line here. So you do see these regions that are below that line, which are fairly significant in the helicity. And I was hoping that if I did the helicity dissipation, which is what's in orange here, that I would see something more emphatic, that I would see things on the surfaces. And I didn't see anything telling me what was going on, anything better than what the helicity was on isosurface. However, the helicity transport is very different. It picks up negative, looking for places with negative helicity transport. And so I have 3 places here, which are identified by the 3 parts of the trefoil, where reconnection would happen. And so this is the same figure again. Emphasizing these points again before I go on. And so this is what I've been playing with. It's a rather tedious project to do these things. But once I have these points here, which are all in dark magenta, indicating the minimum of the helicity flux. And then these lines are indicating points on the opposite side. So the trefoil is two loops. It's equivalent. Sorry, it's either a 3-2 knot or a 2-3 knot, depending on the way you look at it. And I always look on it as a 2-3 knot with two loops, and they go up and down each other 3 times. But if you look at it the other way, it's 2 loops. It's twice. So once I know where these positions of negative helicity flux are located, I find the positions on the other loop, which those points are presumably going to be reconnected. So that's in these oranges lines here. And what I want to do is relate those sets of lines to what I see in other properties. So here is the maximum of vorticity. So, 1, 2, because in this case, I initialized my trajectory at a maximum vorticity, which is equivalent to maximum helicity at this point in time. That point and that point are identical. So it's 1, 2, 3. Okay. And these minima in the helicity flux are strongly associated with the maximum, just these 3 locations. And then we get helicity. So there's a maximum helicity, there's a local maximum helicity. And the opposite signs are the other side, but this is the helicity dissipation. And so all of those 1, 2, 3, the 3 minimum of that. So remember, if you're going to get positive helicity increase, you have negative helicity dissipation. So they're all to the left of the points that are opposite there. So this is just a way of being able to relate different properties along the vortex lines so we understand what's going on. And what about entropy production? So that's in green here. And what's interesting is that where that is negative, remember entropy production, positive or negative. Overall, at this time, with my calculations, it's positive. But where it's negative is where these minimum helicity flux are located. So what is controlling the helicity flux is compression zones along the vortices. And it's where those are happening that you're having this transport of helicity. One direction and negative helicity going in another direction. And understanding that is crucial if we can understand this stuff in terms of this is when reconnections happen. So basically the picture that I just showed you in the middle of where it's developing this reconnection, that holds up until just before this time. And then at the time of reconnection, these positions of the flux are sort of no longer relevant. You don't need to transport negative helicity into spots that make you impact. Whatever's happening at the reconnection sites is already has all the negative helicity needs. And so what you at this point now, what really matters is positions of the negatives of the helicity dissipation, 1, 2, 3. There are a whole bunch of them. It's not a simple thing. And there's really no correspondence here and there. But that's what reconnection is supposed to be about. It's a point at which these nice simple things are being easy to see. So that is essentially where I wanted to go. I have all sorts of other things to discuss when I come back. So I have a responsibility of my daughter's looking at the see where I have to take them. It's 2 days. She works for hours. So we can talk about this 2 weeks, but I wanted to say something about what I've been up to get my own brain focused on this. And we can talk about some of this at lunch or when we get back, and then I will be back here for the meeting when it starts. Thank you.
I was wondering how important the global topology is. I mean, could you start, say, with 2 interlocked links? That, just 2 loops that are linked and see kind of similar.
Yeah, definitely. So the picture I showed you from Zhao and Scalo is actually top line is the Turco, bottom line is the length, I think it's called topological. And that's the original Gauss thinking, which of course we know all about because of Maxwell, because he was the one who discovered it in Gauss's folios after having already derived it himself.
You certainly conclude that energy dissipations only might increase the demand size. Plus, when you increase the demand size, you increase the speed. So
No, so trefoil amount I can put in a domain, periodic domain, and it's compact. Because the energy and the entropy both die to 0 very rapidly as you go outside it. So if you define entropy as the volume integral of the vorticity squared, doesn't matter if your box is this big or that big, it's the same entropy. And that is the definition I'm using of entropy. Now, what is causing, why do I have to make the box bigger? So there's something going on. These are 4 versions of this. Oh, this is. Which time is that? Yeah, this is the beginning. So what happens if the perturbed initial conditions is that I get a reconnection here developing, and I get these negative helicity sheets coming out. So you have this thing coming together, but something's being spread out between the vortices, sheet-like thing. And then the next, this reconnection is sort of already done. This is one that's happening. This is another vortex sheet. And then there's a third one that's going to be about to begin here, and it does something very different. Okay. Now, 2014, 2015, I had a quantum vortex reconnection paper with a student, Srinivasan. So it's Rai, Kerr, Srinivasan, JFM. We're primarily looking at orthogonal vortices and their interaction. And I mean, there's no definition of helicity in quantum vortexes. That's as helical as you can get. And the interesting that happens as it leads up to reconnection is that in between, as those two vortices are twisting around to get close enough together to connect, there's this vast area where there is a sheet of nearly, in the quantum system, you're talking about very low densities. And what happens is that those sheets of zero, nearly zero density start working their way up the original vortices. And if your periodic box is too fine, they'll start seeing the edges of the periodic box, and the whole operation starts being suppressed. Something like that is happening here. Something is being thrown out from the inside of this non-isotropic reconnection that's going on in the center of the phone. And I don't really know what it is yet completely, but I'm getting hints of what this is. And the only way the dynamics can handle this and keep this process happening is the periodic boundary conditions can't be interfering with what's going on in the trophons. Now, the idea that I have to increase domain size to get convergence is really epsilon in the applied analysis community, because they really want to think about things in two boxes. So we had this discussion with Edwards 2 years ago. I've had a lot of discussions with James Robinson since, and I think I know how to deal with the mathematics. And this is part of which I threw up some slides there of what I'm thinking about, but I'm really, really not prepared to discuss this one time. There is going to be something of the mathematics coming out of this, which is going to be, I will investigate to understand why this is happening, what's driving this. But right now I'm doing just the pre-reconnection stuff, and I'm leaving the numerics and the graphics for post-reconnection stuff till later. I need to get some papers out. This is what it is.
There is a question in the chat. Could you restate the point about the role of twist, right, interconversion, and reconnection in your calculation?
Could I rescale,
Now restate
restate?
the point about the role of twist, the twist and the right, interconversion and reconnection in your calculations.
Okay. My previous work from my 2018 papers, I found that the best estimate for what the helicity was the Wright component, which is essentially Biosipar. Now, Yao and he has a postdoc graduate student in Beijing named Zhang. So Zhang and Yang have a nice paper, 2019. I think it's in physics of fluids, where they essentially redid what I did, and they come to all the same conclusions that only the helicity matters. Now, in my other JFN paper in 2018, I looked at coil vortices, and that's much lower Reynolds numbers than we're talking about here. But the thing about a coil vortices is they are initialized, obviously, with some twist helicity, but invariably the continuum helicity from those initial conditions, and as they evolve until reconnection is the rise times the circulation squared. And it's not a twist. There's no contribution to the twist. I followed the twist. I don't see any transfer of rise to twist. So.
If now let's take Prof.
This afternoon,
We do.
at 4.
Let's see. Sorry, so we don't have a turbulence talk, but there is a talk from another workshop on intermittency release.
And that's in the,
That's by Zoom, I understand they have a